What happens when you make one of BMW's best inline-six engines of all time? You get this. That's right, a straight six screamer known as the S54 B32, and it's a 3.2 litre, making anywhere from 315 to 338 horsepower at 7900 RPM and 341 to 365 Nm at around 4900 RPM, all through the rear wheels. We all know the E46 M3 for sporting this magnificent beamer screamer of a motor, but we mustn't forget the Z3M and Z4M as well, two of the greatest two-seater BMWs of all time. Anyways, in the first ever episode of Motor Mysteries, we're going to take a journey into the S54 motor to find out not only its strengths, such as the awesome 8000 RPM redline, but also its weaknesses, such as the well-known rod bearings and vanos, and why that is the case. With that out of the way, let's begin. If you're familiar with BMW engines, you might think that the S54 shares the same building blocks as the M54, as the S52 in the E46 M3 was based on the M52. But this isn't the case with the S54, as it actually took from the S50 engine that was found in the Euro E46 M3s, and this was by using an iron block and aluminium 4-valve head. This is quite different from the M54, which was constructed almost entirely out of aluminium, including the block and cylinder head, to make 333 horsepower in the E46 M3 with only an extra 0.2 litres of displacement. The crank and connecting rods were forged. Not only that, but swing cast high compression mild aluminium pistons were used, which allowed the engine to make a compression ratio of 11.5 to 1, which was the highest out of any M engine at the time. Let's focus on the power a bit. One of the main goals was for this car to hit the holy grail of power, 100 horsepower per litre, and they were able to do it, at least in the E46 M3 and the Z4M, as those cars made at least 333 horsepower, and divided by 3.2 gives us just over 104 horsepower per litre. This puts it in some esteemed company, namely the F20C from the S2000 and M96 from the 996.2 GT3. So how were they able to do this? With peak power being brought on at 7900 RPM, you might think there's bugger all torque down low like a Honda VTEC engine, but surprisingly enough, it's actually a torquey engine in theory, as it uses an undersquare design that has a slightly larger 87mm bore and 91mm stroke. Here, BMW has struck an excellent balance between power and torque, as the undersquare design allows for the engine to reach its peak torque at a relatively low 4900 RPM for an NA engine, but the forged components and high compression ratio allow the engine to rev very freely. Not only that, but the way it delivers that power is quite impressive as well. With some naturally aspirated engines, especially in the modern era, a lot of the power happens to be at the bottom of the rev range, and then when you push the car, the engine kind of runs out of steam at the top. But here in the S54, it's very linear, as the more you give it, the more you get, which is actually quite hard to do, as engines don't naturally make perfectly linear torque, as we can see here with the GR86, which, like the S54, is also naturally aspirated. As we can see with this dyno chart, you'll notice that a very consistent amount of torque is produced by the S54 from 2700 RPM to 7000 RPM, with only a slight drop off near the top of the rev range. And the power is very consistent as well, so you know exactly what to expect when you're giving it the beans on a twisty mountainous road, unlike other turbo engines. You might be asking, how have BMW fine-tuned the power delivery to be this good? Through using what we call dual vanos, which is carried over from the E46 M3. This system dynamically adjusts the camshaft and valve timing, and in the S54, the intake side uses 35mm valves, whilst the exhaust valves are 30.5mm, whilst the camshafts are 12mm of lift on the intake and exhaust side. Speaking of valves, there are 12 intake and 12 exhaust valves, which are acted on by the pair of hollow camshafts with shimmed finger followers that spin in the cylinder head. These shimmed finger followers help reduce complexity and weight of the valve train. But unfortunately, it's not all roses and daisies for the S54's dual Vanos, which we'll find out in the next section. Now, linear power delivery only makes sense if you have a linear throttle response, and with the S54 using 6 individual throttle bodies that are driven by wire, where each cylinder receives air from its own throttle body, you get great response. But you know what ITBs are best known for? Sound. And with that, let's listen to the stock exhaust this car makes from the cabin as we take a punt through the Seacliff Bridge. Simply lovely, and the drive-by-wire is set up quite well, with a dual mode throttle response control that allows you to choose how fast you want those throttle bodies to be open. This is a great balance between smoothness and responsiveness, as the E46 M3 at the time was of course a luxury sport coupe. In fact, drive-by-wire throttle bodies in the modern era are actually quite tough to get right, with all the emissions regs in the way, so you either get a very touchy throttle response or rev hang. For example, the E46, as we can see here in this graph, has quite a linear torque curve, but if we look at the throttle response curve, all of the torque is available even when you give it only 40% throttle. So now we've touched on power, but how can we ensure that the engine doesn't blow up on track due to oil starvation? By ensuring that oil is constantly supplied through a two-stage oil pump that is chain driven off the nitrate coated crankshaft, which uses 12 counterweights. The oil pump pulls its feed from the rear oil pan sump. To ensure the sump is filled to the brim with oil, even under braking, the scavenge pump, which sits in the forward portion of the oil pump housing, uses a smaller oil pickup at the front of the sump to feed the main pickup as the oil sloshes forward under braking. Not only do these dual pickups stop your engine from starving itself of oil, like Manchester City if the FA relegated them to Football League 2, but they also help the oil squirters continuously cool the undersides of the pistons, so you don't run into overheating problems on track. We have power, torque and a properly good oiling system for the track, but how can we ensure that the engine can think on its own? By using an engine management software known as the Siemens S54, which features two 32-bit microcontrollers capable of 25 million calculations per second, while also allowing for the S54 switch to fully electric throttle control and emissions optimizations. This software adjusts from ignition timing, fuel injection metering, cooling and even shifting behavior when equipped with the SMG gearbox. Before we get onto what goes wrong and why, we can't end this section off without briefly going over the S54 B32 HP that was in the M3 CSL. It made 360 horsepower and 370 Nm of torque, and it got some pretty beefy upgrades aside from being lighter than the normal S54. These include a massive carbon fiber intake plenum that completely deletes the normal mass airflow meter, instead relying on the DME directly for air draw calculations, modified camshafts and exhaust valves, and a revised DME. But no one engine is 100% perfect, and with that, let's move on to the design defects of the S54. The elephant in the room, rod bearing failures. Boy, if we almost had all the older M cars in one room, we'd have enough elephants to fill up a zoo. So, what did BMW do wrong here? The usual suspect, like Kaiser Sose, is of course the bearing clearances being way too low at 0.001 inches compared to the industry standard 0.0025. We suspect this was to try and reduce the risk of rod knock that came with the high compression ratio that the S54 was running from the factory, as it was a port injection design. This is why why rod bearings aren't really an issue in the modern direct injected BMW engines such as the S55, as they used direct injection, and by allowing fuel to shoot directly inside the cylinder, rod knock isn't very likely. The next design flaw the rod bearings had was that they were made to use oil with a high ZDDP content, which was basically past the time by the time the E46 M3 came out due to emissions reasons. Remember how I said it wasn't all roses and daisies when it came to the S54's Vanos? And the first Vanos issue that comes to mind is the exhaust camshaft hubtab failure, which is due to the opening in the back of the disc in which the hubtabs were fit, being 1mm oversized. This was to make the Vanos installation easier for mechanics and the like, but they overlooked that broken tabs can break the Vanos pump's drive as they get sucked into the oil pump disc. The next Vanos issue is regarding the sealing plate between the Vanos unit and the solenoid block that can shrink and flatten over time through prolonged exposure to the heat, letting oil pass by. This was made out of a rubber material known as Buna, which was oil resistant and a very common elastomer at the time. But the issue is Buna had an operational limit of 212 degrees Fahrenheit, which is well below the temps found in every internal combustion engine, meaning the seals will eventually shrink and flatten through exposure to a heat, allowing the oil to pass by. The last engine defect we'll cover is regarding the timing chain system, which is almost perfect, if not for the upper exhaust side timing chain guide. Due to the cylinder arrangement and firing order, the timing chain doesn't actually rotate evenly, so the extra chain movement on the exhaust side puts enough pressure to wear the upper guides quite quickly. And as we all know, broken timing chain guides are bad news, as that means the timing chain will eventually go loose. So you can clearly see here that in typical BMW fashion, they've made quite a few engine design decisions that make sense in theory, but not when we talk about real world durability. And with that, let's head into the concluding remarks. Overall, how can we wrap up the curious case of the BMW S54? From the design standpoint, it is truly an engineering marvel, and we definitely consider it one of BMW's best ever engines, as it strikes a balletic balance between refinement down low and a raw, responsive, race-bred feel up high in the rev range, as well as a properly solid oiling system which doesn't starve the engine of oil on a twisty high G racetrack. But of course, there are trade-offs that the aftermarket has luckily addressed. If you stayed until the end, thank you so much. If you've got any other engines you'd like us to deep dive, let us know in the comments. Much love to you all, and I'll see you in a bit.